knows to Leo, and they've been started doing diagrammatics in the previous lecture. And so basically, we're going to study how to obtain Zor average conductivity in terms of averages of retarded and advanced Green's functions. So we express the conductivity in terms of this response kernel Q of a current to external vector potential. And this response kernel has two terms, the magnetic contribution and the gradient contribution. And at zero frequency, in normal metals, we expect cancellation between the two terms. And this trick is used in diagrams in order to improve. Okay, so maybe I should say it like this: that the full expression involves integration over all energies. So it involves states at the Fermi surface, or near the Fermi surface, and below it. We have to integrate over all energies. And on the other hand, we can actually simplify this expression and reduce it to average of product of Green's functions near the Fermi energy, because only those electrons near the Fermi energy contribute to transport. And so we'll see that it comes out exactly in this form. And so we formally rewrite this diamagnetic contribution as this gradient term evaluated at zero frequency, and we subtract it. And as a result, this term pi that includes here is basically a product of two Green's functions with the current vertex. Okay. And here, in this form, I have not assumed Zor averaging, so I don't assume that the Green's functions depend only on the coordinate difference. They depend separately on p and p prime, two momenta. So here, this should be thought of as the vertex corresponding to the observable, the current here. And p prime is the vertex that couples to the external vector potential. It's also a current vertex. And when we order, what we're interested in is the Zor average conductivity. So we're going to average this product of Green's functions, which enter this quantity pi, over Zor. And so this last line really expresses Zor average. Zor average.
So you actually probably want to leave the door open. It gets really hot.
Okay.
So I think it's better to be cool than.
And so the advantage of this form is the improved convergence of the integral. Notice that here we have this exponential factor which arises from the ordering of operators in the current. So the current vertex is psi dagger psi, and if you want to express it in terms of the Green's function, it has to be a certain order of times in the Green's function, and so that's what gives rise to this. So this eta is the time, infinitesimal time difference. Okay, and so if in this formula there are two types of integration over momenta and energy. And in order to, if you just forget about this factor and integrate over energy last, you will find out that this expression is formally divergent. And this divergence comes from large momentum. And these states are empty. So therefore, physically, they do not contribute. But to see that, you have to first perform the energy integral, then only the occupied states will contribute. You will get a convergent expression, and after that, you'll be able to integrate over momenta. However, in disorder, we sort of first integrate over momenta, average over impurities, and so it is what we are, basically we are trying to use this subtraction, this trick, in order to improve convergence of the integrals over momenta. Upon this subtraction, this quantity, the difference between pi at finite frequency and zero frequency, will converge at large momenta, and then we don't have to keep this exponential factor in order to ensure convergence. And that's why I dropped it in this last expression. And that's the formula that is much more convenient for using, for applications to disordered systems. One other simplification that occurs here is that it turns out that the disorder average difference if you evaluate it approximately, which we're going to do, will vanish unless epsilon plus, this epsilon plus omega over 2, is above the Fermi energy and epsilon minus is below. So there are two cases. So roughly, I want to say that there is the frequency axis, there is the Fermi energy, and let's say this is our frequency, epsilon, and we have epsilon plus, epsilon minus are these two energies split by the difference. So if both of them are below the Fermi energy, this difference will vanish, or if both are above the Fermi energy. And so the only range of energy integration that contributes is the range in which energy is very close to the Fermi energy epsilon, and so that epsilon plus is above the Fermi energy and epsilon minus is below. Physically, this corresponds to excitations of electrons across the Fermi surface from occupied states to empty states. And in this frequency range, we will find that this expression is practically independent of the energy epsilon. And therefore, this frequency integration will simply give us omega over 2 pi. So it can be easily done. So I'll do that now. And so we'll see that explicitly we will find that this kernel will be proportional to the frequency because simply of the width of the window of the energy integral. And then when we divide by the frequency to get the conductivity, we'll see that the conductivity will be expressed in terms of simply averaged difference of these current relations evaluated near the Fermi energy. So
I don't think I see where the Fermi energy appears in this expression. Are you saying that the occupation is something that is not written on the blackboard, but I mean the occupation of the state is not included in the, it's not explicitly written there, but we...
No, it isn't. Okay, so the occupancy, okay, let me maybe write a few more formulas. So these are many-body Green's functions. Okay. Maybe the following thing will help that I have failed to say. That we are actually studying a many-body response, right? And so generally we're using many-body diagram technique. What I want to say that is that for non-interacting electrons, we can reduce the problem only to the study of propagators, to a single particle problem. And so it will be, maybe I'll say like this. Let's write this Green's function for in a clean case, where it's just a function of epsilon and p. The epsilon minus psi p plus I delta sigma epsilon. So here, positive energies correspond to energies above the Fermi. So energy is counted from the Fermi energy. So the occupancy comes here. Okay. So if you perform this energy integration, this energy integral will know about whether the state is occupied or not, and that's how you express observables. So in a sense, this Green's function carries information about both occupancy and propagation of the electron. And so we will kind of separate the two problems, occupancy and propagation, and reduce it only to the study of propagators, single particle propagators in this order. And I think it will become clear. Have I answered somewhat the question?
This is an unordered Green's function, right? So it's not a.
These are time-ordered Green's functions. So these are G is a. In this case, is.
That's all problem.
They're time-ordered, but we will reduce them to recurrent and advanced Green's function. Okay. So the time ordering leads to this choice of epsilon, that the sign of the imaginary part depends on epsilon for retarded and advanced form. Okay.
But it seems like that epsilon eta, if eta is, you choose eta to be positive, then it automatically, typically you use that with a particular ordering in the time ordered Green's function.
Right. But it's only at the observable. So I'm saying that we are studying the current relation function, right? So it's two current operators, and we have to make sure from the Hamiltonian when you perturb, they automatically come out as time order. But in the observable, all you're doing is you're evaluating essentially Green's function perturbability, right? And then you put an observable. And that's where this factor comes in. But the rest is evaluation of the Green's function itself. And here we have to use time order.
Just because of the diagrammatic
Yes.
scale.
And I'm considering 0.
Can I have 2 quick questions?
Yes.
Just notationally, what is this psi sub p?
Psi sub p is epsilon, energy counted from the Fermi energy.
Oh, that's not epsilon.
P squared over 2m minus.
P squared over, okay, so psi p is p squared over 2m minus mu, and mu is equal to 10.
And then the second question is, for those of us less familiar with diagrams, can you explain the physical meaning behind this pi vector?
Physical meaning. I would like you to think of it as follows. So the current itself should be expressed in terms of this psi average psi, right? And here you put this current operator derivatives. And so diagrammatically, it's represented in terms of the Green's function at coinciding times. Okay. So here you would introduce this current vertex, which takes the derivative on one coordinate and the other, and this is the vertex. And then the diagram technique is basically a perturbation theory to Green's functions. Okay. And so to first order, the Green's function, the unperturbed Green's function, right, sorry, maybe this will help. So psi dagger, right, it's represented by an arrow. You create an electron at this point and you propagate it, and you find the amplitude of propagation, which is given by this time order truck. So the full Green's function, perturbed one, can be written as the unperturbed Green's function in the absence of perturbation, plus if you have a perturbation to the Hamiltonian, which is a single particle perturbation, namely coupling of the vector potential to the current, you get the vertex. And therefore, this diagram, so to 0th order, it gives you 0 current in the ground state, and then to 2nd order, you have this perturbation, the Green's function coming from the coupling to the external vector potential, and then you compute the observer. Okay. And so what this object describes is a perturbed Green's function. So you have an electron propagating, then it couples, basically accelerated by the external field, and then it comes out here slightly.
So I should think of that as that unwrapped kind of
Unwrapped
together
Green's
version
function,
of that
precisely.
second Green's function there. Yeah. Okay.
Wait, also, I think physically, it's proportional to the response at final momentum, final energy.
Yeah, so right now, yes, but here I want to specialize to 0 momentum, so uniform current, and yes, finite frequency. So what we do is we sort of accelerate electron at an electron at a finite frequency, and so that's why when we had, forget, I think here I have, so, so maybe it's better correct like this. So the energy of the electron is epsilon minus, and then here it increases by the frequency of the external field. Okay, so maybe, right, this is G. So this is the time-ordered Green's function, the function of epsilon. If I have a single particle Hamiltonian, H, it can be written in this form. And depending on whether the sign of energy is positive or negative, that is physically whether the energy is above the Fermi energy or below, the only difference is this sign of the infinitesimal imaginary particles. Okay, and so here I want to write it now in terms of the retarded or advanced Green's functions. So in the retarded Green's function, the infinitesimal imaginary part is positive, in the advanced it's negative. Even though in many-body diagram technique, the retarded Green's function corresponds to an anti-commutator of operators, this form is easy now for non-interacting electrons. So you see that you simply have a resolvent of the propagator, and you simply choose whether you have a propagation forward in time or backward in time because of this. So, mistake. Okay, so that's why basically they describe single particle propagation of an electron, and these functions don't know anything about many body states. It's just this quantity refers to a single particle Hamiltonian. So H is equal to H naught plus the vector potential, plus the, let's say, disorder potential V, and H naught will be written as P squared over 2M minus mu. Okay. So
The difference between top line and bottom line is positive energy, negative energy.
Thank you. Yes, sorry. And so that's why when we are going to integrate over energy, we will simply separate the total integral into several intervals, and we'll express the time-ordered Green's functions in terms of retarded and advanced. Basically, we just take the single particle evolution operator, e to the negative IHT, and Fourier transform it, and that's the retarded and advanced Green's functions, right? So I think it's better to not think of the retarded and advanced Green's functions as these anti-commutators, but in our simple case, they simply describe Feynman amplitudes of single electron propagation. Okay, and so if you believe me that the only relevant integration region are frequencies within the strip omega in the Fermi energy, then the expression for the conductivity we will get is the following. Okay, so what I did here, I expressed this pi in terms of the Green's functions, and then I just simply demanded that epsilon plus be above the Fermi energy, and so therefore one of the Green's functions corresponds to GR. Epsilon minus is below the Fermi energy, therefore it corresponds to GA. And here, both of the Green's functions are say, GA.
So about this restriction of the integration to be just near the Fermi energy. So can you comment maybe about this issue? Because I remember you have to somehow have that this is valid for the real part of the conductivity, right? But the imaginary part can have contributions very far from this window, right? Or
No.
no?
No, so this, okay, we will get, you can get the imaginary, so for example, through the connectivity that will come out of this expression will be q e squared mu d, and then 1, I think minus I omega tau. So at finite frequency, you will get not only the real part of the connectivity, but the imaginary part as well. I mean, this cancellation is sort of exact at zero frequency. There are some issues. If you're talking, so for example, if you renormalize so if you calculate the self-energy correction, it has a real part from this order and imaginary part. And yes, we will only concentrate on the imaginary part of this order. Here, I think we're okay.
Can you say what's the connection of the formula to the formula?
No, I'm just saying that I'm stating the result. Okay. Sorry. This is and I forgot the average. This is just our average. This expression captures quantum corrections in principle. Weak localization. It's all about how to average these Green's functions. If we evaluate in the leading semi-classical approximation, we get the true result, which is frequency dependent. So even though we integrated, so the only assumption here is that there is nothing special, that this average is weakly dependent on the energy near the Fermi energy. So therefore, integration over epsilon simply gives you the width of the integral where the expression doesn't vanish. And after that, we still get a frequency-dependent conductivity where frequency simply comes as an energy difference between the retarded and advanced Green's function.
Why is it retarded minus advanced and not retarded minus retarded?
Doesn't.
Because E is 0, it doesn't matter.
The zero.
Well,
Yeah, if zero doesn't matter, right? It's usually expressed that way. It doesn't matter. Result in terms of the result. Moreover, the way in which we are going to evaluate it, as I said, we're going to approximately evaluate the momentum integrals, and so this will vanish. So the only thing that will matter is the product of GRG. Okay.
So this is still an approximate expression in the sense of you have to talk about this window and the slope. There are corrections to the gradient of GR somehow in omega. If you had to pull out this overall omega factor, you can for 1 over omega, the definition of conductivity. You know, that you said it's proportional to.
Yes, so basically this, what I want to say is that if you just average this expression as a function of frequency, as a function of energy, you will, in this approximate way, I'll say what exactly I mean. So it's a quasi-classical evaluation of the momentum integrals. Then what you find is that it will, say if this is zero energy, it will vanish for positive energies, negative energies, and only in this narrow energy interval you'll get a non-vanishing result. Here, and within that energy window, so basically what matters is the dependence of this average on epsilon will be on the scale of the Fermi energy. Okay? And so with this accuracy of omega divided by epsilon Fermi, it's constant, and we drop. So we will use this kind of one KFL parameter, epsilon omega over epsilon Fermi will be much smaller than 1. This is maybe. This is
And just quickly, if I had a single disorder realization, would this be an exact expression for the connectivity if I just remove the disorder averaging?
yes. Yeah, so far, the only thing yes. Its usefulness, however, it comes from disorder averaging and practically. And approximate evaluation of momentum integrals, okay, that's what we are going to do. We will, I don't know if we'll do it in the lecture, but there is an exercise, you can do it as an exercise, it's in the notes. You can actually check explicitly within this diagram technique, this cancellation between the diagonal.
In your pi, you have g of epsilon plus and then p and then g of epsilon minus. And you said epsilon plus is epsilon plus omega and the other one is epsilon minus omega. Then why you don't have it?
I could have done the same thing. Again, here, I shifted epsilon by omega over 2. But you can write it in many equivalent ways. Okay, so now we have to average this over disorder, and I find it again. I think the simplicity, the usefulness of this expression is in simplicity of dealing with this resultants of single particle operators rather than dealing with many body Green's functions and operators. Okay, so what we're going to do is we're going to average. First of all, expand the retarded and advanced Green's functions in the disorder. So our Hamiltonian is written as the free Hamiltonian p squared over 2m minus mu plus v. And we are going to assume that disorder is weak, in a sense that the impurity potential is smaller than the Fermi energy. And we're going to develop this Green's function in terms of the series in the external potential, and so then this G, or this R, epsilon will be written as G naught R A epsilon times sum over n equals 0 to infinity. So it's basically it's called geometric series. Diagrammatically, it's written as plus. So unperturbed Green's function plus impurity vertex potential, another one plus. So here, each insertion of the external potential is denoted by a cross. That's why it's called a cross diagram technique. And
So just to clarify, these straight lines that you're drawing now, they're different than the straight lines earlier because they're
yes,
free as in just H naught, no disorder.
yes. So these are kind of disorder-specific Green's function. Then what we're doing, we are averaging this. And what I'm now explaining is how to, let's draw them by kind of fat lines for disorder-specific, but then there is more. We have to average that over diagram over disorder. And so this fat Green's function is a sum. Fat disorder-specific Green's function is sum expressed in terms of G naught. Okay, and then let's just maybe draw a couple of diagrams. So basically, what we have to do is put a bunch of impurity crosses in each of the Green's functions and then average. Okay? So how do we average? we say that this external potential is created by impurities. And so little u here will be a potential of a single impurity and centered at R sub A. And we assume that these impurities are sprinkled at random, and we average over impurity positions. So, for example, in momentum space, this V of Q, the Fourier transform of this potential will be again sum over A, U of Q times e to the I Q dot RA, where Q is the momentum transfer scattering. And we see that depending on the position, this amplitude of impurity scattering has this random phase factor. And so when we average over the positions of impurities, the impurity amplitude becomes a random number, and on average it vanishes. When we square, the variance of the random potential does not. And in a homogeneously disordered system, V Q prime will be 2 pi Q delta of Q plus Q prime times some variance which is denoted by W of Q, and W of Q the variance of the potential is related to the impurity concentration, right? And the Fourier transform amplitude of a potential with single impurity. Okay. And so, and we're going to assume two things. We're going to make two approximations. First of all, we will treat the scattering in the Born approximation. We'll assume that potential of single impurity is weak enough to do that. And secondly, we assume that these impurities are sufficiently sparse in space so that we don't need to worry about the higher moments of the potential. And so we will assume that we get simply a Gaussian impurity potential. It's completely characterized by by the variance, and we neglect all the higher order cumulants. And so averaging over this potential in this approximation will simply correspond to all possible contractions, pairwise contractions between crosses. And so what we're going to do is connect, first of all, expand each Green's function in crosses, and then connect crosses in pairwise in every possible way. So,
Is it true that if you go for arbitrary dimension instead of 3, then the only replacement would be to replace the 3 by D?
yes.
And the rest is taken equal, yeah?
But later, yes, but I want to stick to 3 dimensions and conceptually things are. Okay? And so here it's important to distinguish between, so first of all, it's important to say that what we will need for the average conductivity is not just the average Green's function, but the average product of GR and GA. And so therefore, some of the contractions will be within the same Green's function, and they will simply correspond to averaging single GR or GA over disorder. But there will also be contractions between different Green's functions. Okay, and both will need to be taken into account. But now let me start. Right, and I think the important thing is that the average Green's function is a short-range object in space. It will decay exponentially in the scale of the mean free path, but the products will propagate to long distances, and they will describe classical evolution.
So are we assuming that each impurity gives rise to the same impurity potential?
Yeah, we assume for simplicity
So you
identical
use-
impurities, right? But maybe it's one way to think of it. Another way to think of it is that, let's say that this potential is random, Gaussian, and the correlation function depends only on the distance, and so in a sense this W is the Fourier transform of the correlation function of this order. So let's.
So right now you can't, this factor you talked about, the difference between transport versus gathering
It's still
time.
here.
It's all in here,
Yes.
and it's just how you connect up the.
No, the connection way will be the same, but so basically, so the fact that W depends on Q, it means that the scatter amplitude will depend on the momentum transfer, and therefore, in general, transport mean free time will be different from the output mean free time. But if we have a short range delta correlated disorder, this W will be independent of Q, and in that case, there is no difference.
I see,
Okay, so let's now discuss this average Green's function. I will denote it by bar. Good, and so this is the first diagram which will give rise to a non-vector. Okay, maybe that's what relates to your question. So if the impurity potential has a non-vanishing average, then we cannot say that the average is zero. Right? It will give us some kind of shift in the average energy, and this will give rise to a real part of self-energy. Okay. And then we will ignore it. It can be absorbed into the chemical potential, shift of the chemical potential. But the essential part will come from here. We'll see the self-energy arising in this disorder average Green's function will acquire an imaginary part, and that's something kind of a qualitatively new aspect, and this will be essential for disorder. Okay, so let's just evaluate self-energy. So maybe I'll write like I said. G bar retarded over past. Upon averaging, our Green's function will again be dependent only on the coordinate difference, and so we can just use momentum representation, and it will be of the form e to the negative psi p, epsilon minus psi p minus sigma RA. We'll see that this is independent of anything. And so, in a sense, this block will correspond to a self-energy. Lowest order contribution to self-energy. So let's find it. So as I said, this right. So it's this line, the disorder, the variance of the external potential will correspond to two crosses connected by a dashed line, and what we have is a momentum q running along that line. Okay, so in this diagram, our, let's say in general, Green's function will depend on the momentum that comes in. Here we have a vector q and momentum p minus q prime.
Can they go in the same? Sorry.
We'll start with
Should those arrows be going in the same direction, like going in opposite directions, or should they be going like in a?
okay, good. So arrows are meaningful. So in fact, for this function, it doesn't matter because it's a real object.
Okay.
They're meaningful when you have a kind of difference between psi diagram psi. But you're, yes, depends on, the only thing you have to satisfy is momentum conservation. So if this is incoming momentum p, if this is p minus q, then q should run this way Okay, so you should think of it as this way. If I want to put a plus sign, I can. Okay, and then, so to save time, let me start with point-like impurities. Okay. And then I'll discuss the generalization to the general disorder. So I will assume that W is independent of Q. This function, sorry, the self-energy will simply correspond to integral d, let me just call it p prime, the momentum W independent of anything, and then here we have epsilon minus psi p plus minus r. Okay. So again, in general, this first of all, this integral is divergent, and therefore, but the divergence comes only in the real part. And as I said, I don't want to deal with it. So the jargon is we're going to normalize the chemical potential, and it's not going to matter. So what we're after really is the imaginary part of self-energy, and here I can. So this imaginary part comes from energies psi p equals to 0. So we will see that epsilon will be near 0, near the Fermi energy, and so psi p, p squared over 2m minus mu should also be close to 0 in order to get this. And so therefore I will just evaluate. So let me just state the rule. The integral over p will be replaced by the density of states at energy epsilon times the integral over psi from negative infinity to positive infinity. And so this rule is only good near the Fermi energies. It's terrible at evaluating states away from the Fermi, so near the bottom of the Fermi sea or up at the very top. But it works. So it's basically a linearization of the density of states. And if you do that, then this integral will give you minus plus I pi density of states times W.
Now, where's the, so now you have integral of p prime.
Yeah, let's go to psi prime. So go psi p prime.
But no, one line above. The p.
Thank you. It's just p prime. It's this momentum that runs.
It's just a constant.
Shouldn't you replace the dash in as an I u square?
Okay. In the many-body diagram technique, no, the answer is no in either case. Okay, so in many-body diagram technique, the vertex is negative I, right? But I want to take a kind of more pedestrian approach. I'm just saying that what I'm doing is I'm expanding this in the series, in V. And so my vertex, where is this? It's just V with no I. So it's simpler to think about, but yes, if I think in terms of, okay, maybe the correspondence with many-body diagram technique is the following. Each insertion of the vector of the potential corresponds to negative I, V, and then, but each Green's function, each line corresponds to IG. Okay? And so you get the same result, but I find it easier to think of, not think of the rules of the many-body diagram technique, but somehow say that, okay, we've used all we need from many-body diagram technique. Now we're just dealing with GR and GA, which are given by these simple expressions. And so all the vertices no longer involve I's.
So can this divergence of the real part be sort of cured by this W, the values?
No. Okay, so only if you have some weird scattering where it's exactly resonant at the Fermi energy, and then if you go below the Fermi energy or above, it vanishes. Then yes. So maybe I should say yes. If eventually at very high momenta, if the scattering cross section goes to zero, yes, it will help. But then still, at least at low energies, you will have to integrate over all states, including those that are occupied.
So to claim that for point-like scatters, the self-energy is independent of momentum?
Yes.
So then, I mean, you shifted P, you had P, you had integral over P plus Q, you had integral over Q, and you shifted, so in other words, that energy was a function of P plus Q, and you integrated over Q, and you shifted P plus Q to P prime. But maybe you already mentioned this, but if the integral is UV divergent, then it depends on the short scale cutoff. And so that shift.
Okay, but this divergence, okay, first of all, the divergence involves the real part.
Right.
Somehow it misses the whole point, and I don't want to discuss it. But if your question is what was,
no, I guess I guess it's not a problem because it's just you just give it some real part that you can again absorb it in chemical kinetic.
yes, exactly. Whereas the imaginary part in this psi integral is convergent, right? Because of 1 over psi squared. That's a convergent integral, and it's dominated by values of momentum close to the Fermi surface. And it's basically, I think there's a nice physics. So I like to think of it as follows: that we have an incoming momentum p. Of course, we have an amplitude of scattering from any momentum state to any momentum state. It doesn't have to be on-shell scattering, right? However, if this electron propagates out to long distances, effectively it puts itself on shell, this long motion after that. And the on-shell scattering is precisely this resonance where the imaginary part comes from. Okay? So therefore, this imaginary part describes real scattering processes as opposed to scattering to virtual states. Okay? And whenever we deal with disorder, so the relevant, so if you wish, the distance to which the electron propagates before coming back is at least the mean-free path. And so because it's long, we are off shell, and so. And now coming back to your question, even if I included the momentum dependence of the empiric scattering, the self-energy again would turn out to be independent of momentum, simply because of the isotropy of the Fermi surface, and then.
So the idea is that if we try and calculate the like odd number of cross diagrams, it's the same thing. So we're just excluding them by that argument that they're not zero.
Yeah, if you have an odd number of crosses by our assumption it's zero, it's only you need to have an even number of crosses.
Can you comment on the imaginary? So you get this imaginary part of the Green's function. So
the imaginary part of the self-energy.
Of self-energy. So then the Green's function is. So the decay is not. It's just a way to represent this. So all the scattering is elastic, right?
Yes.
But it just represents the fact that momentum is not, it's scattering out of those momentum states. It's a rate of scattering out of those momentums.
Yes, thank you. I'll comment that. Excellent question. So let me just state what we got. I mean, somehow what we got is a finite imaginary part. Let's put it in. I will jump in ahead. I will just replace it by plus minus I over 2 tau. Because we'll see that that's exactly what it corresponds to. And tau is precisely this out scattering time. And so, in a way, what we are getting is that in the unperturbed Green's function, disorder unaveraged Green's function, we have this infinitesimal imaginary part, which is positive for retarded Green's function, negative for advanced Green's functions. once we average it over disorder, this infinitesimal imaginary part will become finite, and the sign will be the same as the sign. So for GR, it will go one way, A the other way. And so it sort of, it reminds me of a phenomenon of spontaneous symmetry breaking, where this I eta will go to I over 2 tau, will become finite. And so, so somehow this self-energy wants to be finite, but it doesn't know whether it wants to be a plus I over 2 tau or minus. And this infinitesimal symmetry breaking field, eta, in the Green's function tells you which way it should point. And so this symmetry breaking between retarded and advanced Green's functions is what's at the heart of the sigma model description of disordered systems. So we'll see there's a field theory where there is a spontaneous symmetry breaking, and diffusive modes of electron propagation corresponds to Goldstone bosons in this theory. Now, to Leo's question, I want to say, so what is the meaning of this disordered average Green's function? So first of all, the clean Green's function, say, one tries with factors, there's m over pi's, but basically it's e to the I k epsilon r. So for human energy, we have an electron momentum that corresponds to it, and the Green's function decays the power law. 3 is 1 over r, but it oscillates in space. Once we put impurities in, you can, I mean, what you see is that in addition there is a factor negative r over 2l, where l is the mean free path corresponding to this tau, and so the average Green's function will decay exponentially. But however, if you look at the specific realization of disorder, this will not be the case. It's still, in a given realization of disorder, the Green's function will fall off only as a power law. So you can sort of loosely think of it as 1 over r e to the I k epsilon r plus I phi, where phi is a disorder-specific phase. And this phase oscillates, and when you average over the phase, you get this exponential decay. Okay? But in a given sample, the Green's function never decays exponentially, and therefore, when you look at products like GRGA in diagrams like this, then these phases in GR and GA do not cancel completely, and that's why the products of averages survive to much longer distances, longer than the initial path. Okay. Leo, does it answer?
Yeah, no, it's perfect. It's just sometimes, you see this imagined thing, and the first thing is, well, maybe there's some dissipation.
No, it's not. It's just disorder averaging. That's what it is. So, and so it also tells us that just the average Green's function is a very poor representation for a typical one in the disordered sample, and that's why we have to deal with products of Green's functions rather than average Green's functions in order to extract the physics. And so we will use the classes of diagrams which describe this kind of long-range correlation.
So you said that that second line is what holds for the disorder-specific realization. So what does R mean in that case?
Nothing. I'm just because loosely speaking, you look at the typical Green's function and ask how does it fall off? So it's a random object. It's hard. I would be hard pressed to define what is typical, but kind of loosely speaking, you take a sample, measure these points. What does it look like? And it still falls off as a. It's no longer a function of the difference, but I think it's a good image to have.
And I mean, you could have also just done this. You could have found this tau by Fermi golden rule.
Yes. No, that's okay. This is the Fermi golden. So basically, what we're saying is that look, this what are they called? Linelli or Stokowski formulae, right? Where this is negative plus I pi delta function of epsilon minus psi p. Right. That's what puts you on shell. That's precisely the golden rule. And then here we have a square of the L. So that's precisely this classic.
But it's Born approximation. Okay?
Important. But the golden rule is also.
Okay. Yeah.
So once more about this spontaneous symmetry. So in a specific disorder realization, I cannot think in these terms.
No.
Only if it's the average.
Can I escape this exponential decay of the disorder average ring function by assuming some noise correlation.
No, it's just really hard with this. So basically, it's semi-classical approximation is P1 over KFL is small, and as a result, when you go to large distances, the phase of the direction phase oscillates, and no matter what the disorder is at long distances, the phase will randomize, and the average ring function will be big.
So I have a question about the that formula for a specific disorder realization. It is still long range, right? But if there's
Which formula?
this one, yeah,
This one or
the second one.
Okay.
So if there is localization, this is no longer the formula.
No.
Okay.
Right. So yes, I am talking about okay. So maybe basically I want to think about metals. Okay, and to zeroth order approximation, I just want to rewrite the Drude expression, and but then we'll see that there are corrections to the leading classical approximation. They're small in 1 over KFL, but sometimes they diverge and they lead to weak localization. So we'll approach this kind of question of interferent quantum corrections or quantum effects in transport from the metallic side where motion is semi-classical, and so everything will be small in 1 over KFL, everything non-classical. Right, but so even though it's small, if they're small in 1 over KFL, but they merge with the sample size, they will lead to localization. And in that case, in this language, actually nothing will happen to the disorder average Green's function. Will still decay on the mean free path, but the localization length will be much longer than the mean free path. But the correlator of retarded and advanced Green's function will then decay exponentially. Okay, so maybe the next step is we see that in this lowest order diagram to self-energy we get this factor of 1 over tau, the out in time. What happens if we put more impurity lines in? There is so let me consider a 4th order diagram. There's 2 types of contributions. So the key point I want to make here is the non-crossing approximation. Okay, so this is called a crossing diagram, because these impurity lines will cross, and this is a non-crossing diagram. Both are 4th order impurities, and there's another example. This is not really a correction to self-energy, just a correction to the Green's function. The correction to self-energy would be this. It's called a rainbow series of diagrams, whereas this is a crossing diagram. And so the point is that the rainbow diagram, or this crossing diagram, is small in 1 over KFL in comparison to that one. So you can just check it by explicit calculation, but I like to just argue as follows graphically that in a non-crossing diagram, what we do is P prime, P double prime, and then this is P prime. And so if you, so first of all, I think the following is a good image to have that in this imaginary part of self-energy comes from on-shell scattering processes. So, and by on-shell, really, so what we see that the extent of the Green's function is the mean free path. So therefore, kind of in energy width, so in energy window, this width is 1 over tau. And 1 over tau is much smaller than the Fermi energy. So basically, all this imaginary part comes from momenta in a very narrow, slim shell near the Fermi energy, and the width of this shell is 1 over tau, and that's sort of the essential momentum integration region here. Okay, so in this diagram, so we go in, say, from some initial momentum p, scatter to a momentum p prime, then to another momentum p double prime, and then we go back to p, and then p. Okay, so it's kind of the scattering sequence is like that. Okay. And so therefore, this p is fixed, but we can scatter over, you know, when we integrate over p prime and p double prime, we have a product of independent momentum integrals over the shell. Now let's look at this diagram. So here we have this initial momentum p. We scatter to p prime. Let me now think of kind of momentum transfer q and q prime. So first the electron loses momentum q, then it loses momentum q prime, then it picks up momentum q, and picks up q prime. So we sort of go in this direction. This is momentum q, then this momentum q prime that was given. Then we have to pick up momentum q, and then come back. Okay. And so therefore, only in a narrow region of directions, this momentum lands in the good integration region. So therefore, and so we cannot assume that these two momenta are arbitrary, and we lose directional space. So we get on shell only kind of for very specific realization of momentum transfers, and so the width of this angular integration, of course, is 1 over tau. And so you see that you get a smallness in 1 over epsilon Fermi tau in comparison to this integral. Okay, and so therefore, since we are going to work in a clean metal, we will drop all non-crossing diagrams. And also, this now corresponds to kind of a classical sequence of scatter impurity, and come back. So it's basically, in this process, these two amplitudes correspond to sort of, I think it will become clear, but this is in a sense a classical extension. So we will use it.
You're going to ignore the crossing.
Sorry?
You're going to work with a non-crossing?
We're going to ignore, we're going to start with non-crossing approximation to get kind of classical result, and then we'll add, so all crosses will come as semi-classical corrections there, 1 over KFL, but then there will be an important series of diagrams where this smallness is compensated by something else.
But it's small in tau 1 over...
1 over epsilon Fermi tau or 1 over KFL at the same.
Okay.
So none of the non-crossing diagrams give quantum?
Yes, they give crossing diagrams give quantum curves.
But not the non-crossing ones?
No, I'll argue that. I mean, I'll show that there. We'll get the Boltzmann equation in the crossing. In the non-crossing. Okay. Okay, so I don't have to, maybe I'll qualitatively say what this means. That first of all, if you sound the series of rainbow diagrams, what you can find is that, so basically what you get is sigma will be equal to again 2 crosses on the outside, but inside we have again a whole series of Green's functions. By this, what I mean is this is also a rainbow diagram. So all these are non-crossing diagrams, and so what we have here is the fat Green's function. It's all included, and so I can just write that within this non-crossing approximation, the full expression for sigma is the same as we had for the lowest order perturbation theory, except for the full Green's function. Okay. And so therefore, what I will get is that sigma will be equal to and now I have to solve for it self-consistently, but again, and we are looking for the imaginary part of the self-energy, and what you find is that basically, so this is called the self-consistent Born approximation, and the answer is the same, that self-energy will be plus minus pi over 2 tau. So it doesn't matter whether you just do it to lowest order or not, because you integrate you do the integral by residues.
So, just so I have it clear, so if you had like this diagram, the whole idea is that like the second one is just for normalizing some external leg or something, so you only care about like one rainbow. You know, so like.
What do you mean by the second one?
So like you could have, right? You could have
you
two
mean
rainbows, right?
Yes,
So,
but okay, but so that block, okay, self-energy is the block that cannot be cut by kind of a single electron line, right? So that's why, so we sum a whole class of diagrams. We're saying that if you have a series of such things, like this plus this, that's another geometric series, but with sigma as the denominator. And so we basically.
Another question. So, from this self-consistent one, you get a different expression for tau, right? Or
No, the same expression. Yeah.
Then you
Okay.
have to
Let me
take
just.
back
So
the
I guess I'm running out of time. You get the same expression. Moreover, you'll get precisely the classical expression. Right? So the reason is that I want to maybe. So regardless of whether you have point-like derivatives or not, this one or tau will be the classical out realization time. And so roughly it's basically what Leo said, that this diagram, when we write it like this, so here we have two impurity scattering amplitudes, scattering between P and P prime. And then we have to integrate over all momentum P prime. And when we do that, the imaginary part comes from the on-shell scattering. So even though in generally this is just a Born amplitude, it doesn't correspond to a physical scattering cross-section. Once we integrate it here in this diagram, we only integrate over momenta which are on-shell. Okay, and therefore this amplitude can be related to the classical scattering cross-section. So this U will correspond to sigma, differential scattering cross-section, and you are integrating over all directions in the time series.
this assumes that 1 over epsilon tau is small. Sorry, in the expression you have for the full sigma there, don't you need a W to...
Oh, thank you, I do. Right. And in fact, that's where 1 over tau comes from. I think I lost it in the previous expression too. It's basically density of states times W. In 3D, this is MP Fermi, so you get velocity times W. That's 1 over tau.
But don't you miss also the average over the angle?
No, it's in the, okay.
It's in the
This density of states includes integrals over all directions. Okay, so I'm just saying that I integrate over psi and directions, but for point-like scatterers, W is independent of directions, so I just get 4 pi. In more complicated case, I get full scattering cross-section, but no. I'm not sure if I
I don't know because I used to have the
Well, I'm saying that psi here depends on the absolute value of momentum. Right? So therefore, I do integrate over all directions, but the integrand is independent of directions, and for a point like impurities, it is independent, and the density of states includes density of states not only for a specific direction, but includes integration over all surfaces.
The reason why is because it's classical is you only consider the on-shell process.
Precisely, right. And the reason for that is because KFL. So basically, this fact that it's 1 over tau, you can ask how far does it run away? And it runs away to distances of the mean-free path, which are very long in comparison to lambda Fermi, and therefore it's on-shell scattering. So the assumption is that if within this, within momentum, if you change momentum by 1 over L and the scattering cross-section is independent of that, of the magnitude, it only depends on the direction. That's why we're on-shell, and that's why everything's classical. For some very weird impurities, it's not the case, but that's the assumption. We have short-range impurities, and the scattering cross-section depends on the direction of n, but not on the magnitude of n.
Now, why do you equate, oh, sorry.
Okay, so that's it.
So I wanted to ask if you have from very beginning some another self-energy, then we cannot use Sokotski formula for integration, and then we never get this classical result. Yeah? So if we have other processes like interaction or other processes of scattering except of impurities, then we cannot use Sokotski formula, and then we never have this interpretation, easy interpretation and classical result.
Yeah, yes, I can imagine that there are many cases and still. So basically, maybe there are some simplifications in more complicated cases, but yes, to be safe, I just want to stick to non-interacting impurities. And I know that there are definitely examples where real part is important and that treatment is.
Yeah, I understand why you equate on-shell to classical. So on-shell means there's no virtual transition, but couldn't you still have interference and you just have...
No, all I'm saying is that if I want to, okay, so here we just have some scattering amplitude, which is not related to any physical, sorry, it's just it's a matrix element of the perturbation. It doesn't correspond to any physical scattering process, right? We can have P on the Fermi energy and then somewhere else. I'm just saying that in the limit of when KFL is large, we can relate this magnitude W to the physical scattering cross-section. And that's why we can interpret this time tau as the out relaxation time for in the Boltzmann distribution.
Oh, I see. Okay.
Going much slower than I was hoping. Okay, so let's now keep going in this non-crossing approximation, leading water in 1 over KFL. So it's well known that if you want to preserve gauge invariance, so we know that if we solve the problem exactly, we will get gauge invariant result. However, we are making this approximation, and we want to make sure we don't violate gauge invariance in this approximation. And so in diagrams, it's called a conserving approximation. So there are ward identities between self-energy and vertices. And if you approximate both the self-energy and the vertex, but want to preserve gauge invariance, you have to preserve these ward identities between approximate vertices and approximate self-energies. And in practice, I think it has a very simple meaning that if you basically, if you have a certain sequence of diagrams for the Green's function, and then you perturb it by an external potential, you have to perturb the same sequence of diagrams. And then everything will be gauge invariant. So therefore, if we have non-crossing diagrams, So that's called the conservative approximation. So if we only have non-crossing impurity diagrams for the Green's function, and then now we have to put in this external current vertex to perturb the Green's function by interaction with the external field. We can insert it, for example, here between the self-energies, and such diagram will correspond to two fat Green's functions. Or we can insert the external current vertex, let's say here, and that will correspond to the following diagram. I mean, this is a application. So the upshot is that since we didn't allow crossing in self-energy, we also should not include it here. And that's what we're going to do. And so such diagrams are called ladder diagrams. And this sequence of ladder diagrams will give the Boltzmann result.
Excuse me, this is current values or scalar values or any of the two?
It doesn't matter, but in particular, I'll be interested. Okay, here I'll need the current vertex, but no matter what, so you need to take it.
Can you say again, what you're not going to allow what? Non-crossing approximation?
No, right. I will use non-crossing approximation in the vertices.
In the vertex as well as the...
So yeah, these diagrams like that will be excluded in the classical.
But these maximally crossed diagrams will give you something else, right? Like weak localization.
Good. So since you mentioned, let me say what people mean by. So this is a cross diagram, okay? And it's small in 1R KFL for the same reason that I outlined. So the question is, fine, as you allow more crosses, do more crossings come with higher powers of 1R KFL, or do they stay in the same order as 1R KFL? And so maximally crossed diagrams are diagrams like that, where they're all kind of in opposite order, and they're all in the same order, 1R KFL. Okay? So in that sense, but the reason for that is that in reality there's only kind of one crossing, and so if you write this Green's function, this how to do it. Like that. Okay. They actually non-cross, so you only pay once for the crossing, and then you have again sum a series of diagrams. And these are precisely these leading semi-classical corrections, which will give rise to weak localization. Okay, let's now, in this non-crossing approximation, let's see what we get for this correlator in the conductivity. Okay. So first of all, I'm going to already say that I'll draw the diagram and we'll use the average Green's function. So let me denote by these lines or the average Green's function, G bar. And so what we have in the diagram is one current vertex corresponding to the observable. So here we have GR epsilon plus P. Another Green's function, GA epsilon minus, and another vertex P prime here, and we have to average this product over impurities. And so what I'm going to do is I already will write, whenever this line will be written, I will assume disorder average Green's function, which will contain 1 over 2 tau. But in addition, we have to put crosses between the two Green's functions. So that's, these diagrams will tell the difference between the product of averages and the average product. Let me start with point-like impurities. In point-like impurities, so one jargon way of writing this is that we say that these diagrams renormalize the current vertex. Okay. So what we can say is that if we take into account these diagrams, we'll write it by this block. This will be the renormalized vertex, which will still be a vector current, but not quite P. And then we have last GR and GA after this last impurity line. And so the first statement I want to make is that for point-like impurities, this current vertex is not renormalized. So let me state maybe the rules of the disordered identity. W. So this, you basically can express W in terms of this out scattering cross section, and that's the result you get. And it's independent of the momentum transfer. Okay, and then in this diagram, what we have is P prime vertex. And because now this the expression for this impurity line is independent of the momentum transfer, we basically have a separation of this diagram into two independent momentum integrals. One integral over P, another integral over P prime. Okay, so let's just evaluate one of them. So we have this integral Dp. We have this current P. And let's write the expressions for epsilon plus minus psi plus I over tau.
Is that a P multiplying the two?
Yes, P is multiplying the two things.
Okay.
It comes, yeah. Okay, and so this diagram vanishes.
Sorry, is there another momentum?
Sorry?
P is the momentum going through the diagram? Or no?
Yes, P is the momentum going through the diagram, so if I want to write the expression for the full diagram, I'll have the same integral of P prime with also P prime. So, no, right, P is the momentum kind of running in this loop.
Oh, running around, not
Yes, and P prime is the momentum running around, and the two loops are decoupled. Okay? So if the impurity scattering cross-section depended on the momentum transfer, then this integration would be coupled. Okay? And so
there's no momentum running through the diagram, through the wiggly line. Your current response is at zero momentum.
Yes, exactly. So Q, the incoming momentum is zero. So we consider it from anyway, so I don't want to finish the expression. We have basically a product of two identical expressions which vanish. Okay? But it's clear that they vanish only for point-like impurities, and if the impurities, if the scattering cross-section depends on the momentum transfer, they become coupled, and we have to solve this equation. I have it in the notes. I can just maybe let me finish the point-like calculation, and I'll state the results for the non-point-like scatterers. you see that all other diagrams vanish, and so the only diagram that is necessary for the conductivity is the diagram where we simply have the average Green's function on the top and the average on the bottom, and the correlations are not important. And this diagram is given by integral dp, p alpha, p beta, and then the same expression, epsilon minus psi p plus I over 2 tau epsilon minus psi p minus plus. You do this so now you see that you can do this integral by residues. So simply replace this integral by mu, and then integral d psi, and then the average of p alpha, p beta over the Fermi surface will be replaced by p Fermi delta alpha beta over d, dimensionality of space squared. And so, and when you, so by order of magnitude, I won't do anything, but so you get p squared, there is m p Fermi squared delta alpha beta, and this integral will give you the density of states times tau. So this is precisely so with numbers you do get the Drude result. So the density of states in 3D is md Fermi. So you'll get exactly E squared density of states times 2 v tau.
Wait, why don't you get a difference of e plus and minus when you went to omega versus 0 limit?
Good. Okay. So, okay. When you do the integral over psi. Say, what? Okay, let's just do this. So let's say epsilon minus psi p. In one case, you have plus omega plus I over tau over 2. In that case, it's epsilon minus psi minus omega plus I over tau over 2. So you will get not just tau, but always combination of that. And so at finite frequency, you get this, you get a complex expression, but when in the diffusive regime, when omega is small in 1 over tau, you get the static Drude conductivity.
Sorry, what's the difference between this calculation done on the left and the right? I mean, what's the actual diagram you've drawn there?
Okay. Here I was considering a next order direction.
Yeah,
right?
and that's first.
Sorry?
Yeah, but on the left.
Right, so the difference is the presence of momentum. Right, so here by energy I have the same expression.
Yeah.
But then it averages over the directions, whereas here I have p alpha, p beta, and that does not average to 0.
Because you've got momentum coming in on the legs, whereas there you have nothing.
Yes, I have two momenta coming in one.
Okay.
It's basically, so I have the same momentum, they're correlated, right?
Yeah.
But this, when I consider pure derealization of the vertex, since the scattering cross section is independent of the incoming momentum, sort of one momentum doesn't know about the other, so momentum memory is lost. But if you have non-point-like impurities and transport mean free time is longer, then upon one impurity scattering, the momentum memory is not completely lost. And so then you have to sum a series of diagrams. You get an equation which is written in the notes. Equation 61. So you just, in this case, you have to solve, so the series of ladder diagrams will give you an integral equation for pi, so this correlator, and it can be solved and screwed into a classical transport equation. And then the difference is that basically this renormalized vertex, instead of p, which is not renormalized by impurity, goes to tau transport over tau times p. And so therefore you still recover the Drude result, accept them in the diffusion constant instead of V Fermi L over D, that goes to V Fermi L transport over. The way it comes out is via this normal relation. And so, therefore, with this understanding, what is typically done in the theory of disorder is that, okay, of course it's easier not to deal with such vertex relocalizations, deal with point-like impurities. In this case, there's no distinction between tau transport and tau, so we will work in that approximation, but the understanding is that wherever you see tau, it should be tau tau. Well, okay, maybe I should. The thing is that there are some